Okay, so like I said in the last video, the software I'm using only allows me to record 15 minutes, and I was a little rushed at the end of that last video. So just to touch on again what I was saying, in this second example here, the 12 million number, there is no decimal point. If there was a decimal point, it would be right here. Okay, so all of these trailing zeros are coming before the decimal point, which means they are not significant. So none of these are significant. The only significant figures in this number are the 1 and the 2. So it only has 2 significant figures. And the fifth significant figure rule is that leading zeros are not significant. This one is kind of easy because it's always the case. It doesn't matter if there's a decimal point or not. Any zeros that come at the beginning of a number are not significant. So if we have 0.0003, all of these zeros at the beginning, not significant, not significant, not significant, not significant, significant. So it has just one significant figure. Here's another example, 0.418, the 0 at the beginning, not significant. But the 4, the 1, and the 8 are, so it has 3 significant figures. Now, we get into the situation where we have two numbers and we're going to do something mathematically with them. We're going to multiply, divide, add, or subtract. And then it affects the number of significant figures that our answer should have. So when multiplying or dividing numbers, the answer should have the same number of significant figures as the original number we started with had the least number of significant figures. So for example, we have 420 and we're multiplying it by 8.392. So 420, the 4 is significant, the 2 is significant, the 0. Is that significant or not? There's no decimal point. If there was, it would be right here. So the 0 is coming before the decimal point. So we cannot really say that that is significant. So this has 2 significant figures, or sig figs. This number, 8.392, all of these are non-zero. So the 8, the 3, the 9, the 2, they're all significant. It has 4. So the number with the least significant figures that we are using in our multiplication problem is this one, 2 significant figures, which means our answer should only have 2 significant figures. Now, if you punch this into your calculator, 420 times 8.392, your calculator will give you 3,524.64. But we cannot report an answer with that many significant figures. Keeping in mind that the reason for this is because we are assuming that these numbers that we are multiplying came from some type of measurement. We measured something and we could only measure whatever this is to the nearest tens place, 420. It's not 421, it's not 422, it's not 420.001, it's just 420. So we cannot be more accurate than this piece of raw data. And so, although this is what your calculator tells you, this is not the correct answer. The correct answer needs to be rounded off to 2 significant figures. So we want the 3, we want the 5, and then we look at the next number. It's a 2. Okay, so if it was a 5 or above, we would round up. 4 or below, we round down. So it's a 2, so we round down. So we just round off the last 2 places here and make them zeros. So rounding off to 2 significant figures leads us to an answer of 3,500. This will come up throughout the entire semester. And I know from experience that throughout the entire semester, I'm going to continue to have some people that keep putting in answers like this into their homework assignments on Blackboard. They just punch it into their calculator, and then they type in all of those digits that their calculator gives them. But you always, always, always need to use significant figures. And since our number over here of 420 only had 2 significant figures, our answer should only have 2 significant figures. This is correct. This is not. Now, when we are adding or subtracting with significant figures, the rule is slightly different. Basically, we should think of how you were taught to add, or I don't know, this is how I was taught to add. When you're stacking numbers up vertically and you're doing like a hand calculation, you want the decimal points all to line up with each other. Okay? And what we're saying is that the final answer here in an addition or subtraction problem is not dependent on the number of significant figures, but rather where the last significant figure is in terms of the ones place, the tens place, or the tenths, or hundredths, or thousandths. So right here, this 411, it ends right there. There are no significant figures trailing that decimal point. Now the 3.884, it has 3 significant figures past the decimal point. This one has 1 significant figure past the decimal point. This one has, well, the trailing zeros are not significant, but the 5 is, and that's in the, what would that be? Tenths, hundredths, thousandths, 10,000ths place. But the limiting factor in this problem is going to be this first number, because it gets cut off right there. No significant figures after that. So we basically want to chop off all of our numbers at that same point. Okay, so we add them all up and we get 485.8845, but we want to chop off the number of significant, easy for me to say, significant figures right there. So we want to eliminate all of these. Okay, except this number here is an 8. So we're going to round this 5, we're going to round it up to a 6. So this 485.8845 becomes 486. So just keep in mind that when you type problems into a calculator, it will give you probably loads more significant figures than what you really need to report. So what you have to keep in mind that although maybe if you were in a math class and you were asked to divide 2 by 3, you might give 0.666. You might just write a bunch of those, or maybe you'd even put 0.6 with a bar over it to indicate it's repeating. But in a physics class, we are assuming these numbers are data that came from some type of measurement. And here we have 2 significant figures, and here we have 2 significant figures, and we're dividing. Therefore, our answer should have 2 significant figures. Okay, so our answer really should be 0.67. All right, we're rounding up this 6 here because the following number is greater than 5. We're going to round that up. So 2 significant figures in our answer because each of the numbers over here had 2 significant figures. Now down here, we have an interesting situation here where we have 2.5 times 3.2. Okay, the calculator just shows us that answer is 8. But that's not enough significant figures. Again, we have a number here with 2, another number here with 2 significant figures. Therefore, our answer should have 2 significant figures. We should report this as 8.0, not just 8, but 8.0. So here we have an example. Again, we measured the height and width of a rectangle, we measured as 4.5 and 3.25. We want to multiply those two numbers together to get the area. Which of these answers is correct? Well, we have to look at the number of significant figures. We don't want to go based on what our calculator shows us, but we want to round to the proper number of significant figures. This one's got 2, this one's got 3, therefore this is the limiting number. Our answer should only have 2 significant figures. It should be C, just 15. And there we go, that was the correct answer. All right, let's quickly state the number of significant figures, 1.23. This one's pretty easy, they're all non-zero, so the 1, the 2, and the 3 are all significant. So that's 3 significant figures. Over here we have 0.123. So the 1, the 2, and the 3 are significant. What about this 0? Is it significant or not? Well, it comes at the beginning of the number, so it is not. And finally this one, 0.0123. Well, this is really just the same as the previous one. These come at the beginning, these zeros, that's not significant, that's not significant. It's just the 1, 2, and 3 that are. So we run into an interesting problem here when we have a number, let's say just for example, that this 36,900, we want it to have 5 significant figures. We want all of these numbers to be significant. Okay, it just so happened that we measured something and it came out to be exactly 36,900. If we just write 36,900, then according to our rules of significant figures, these two zeros with the absence of a decimal point are non-significant. So let me write this down, 36,900. If we just write it like that, those are not significant. We only have 3 significant figures, but maybe that's not what we mean to say. So a way we could write this number and make sure that the reader understands that these are significant is to put it into scientific notation. This would be 36, well, we could say, let's go 3.69 and then 0, 0. If we include those zeros in the scientific notation, times 10 to the 4th, that definitely indicates to the reader that these are significant because we included them in our scientific notation. We didn't have to. See, 36,900 can be written as 3.69 times 10 to the 4th, but we chose to put them there. We chose to do that. We didn't have to, but we did. Therefore, they must be significant. So this is how we can tell people that these zeros are in fact significant. Whereas if we just wrote it out as 36,900, that would be unclear. In fact, we would probably assume that they are not significant. So scientific notation is just a way of taking a number and multiplying it by 10 to some power. Now, if we had 3.69 times 10, every time we multiply by 10, we move that decimal place over once. And if we were to do 3.69 times 10 times 10, or multiplying by 10 twice, we would move the decimal place twice. Well, 10 times 10, we could shorten that up by writing it as 10 squared. Okay, so 3.69 times 10 squared is, we just move the decimal point, the number that we have here in the exponent. So when we take 3.69 times 10 to the 4th, 3.69 times 10 to the 4th, we just move this decimal place 4 times. 1, 2, then we have to move it 3, 4, and we put zeros in as placeholders. So that equals 36,900. And I'm about to run out of time, and so we'll resume in the next video.